Hello everyone. In our previous lecture, we have understood what is the meaning of a digital logic and a digital system, and we also understood that a digital signal is essentially a discrete signal in values as well as in time. So, in today's lecture, we will see how this digital signal is obtained and how to do binary representation using digital signals. Okay, and then we will also compare digital system with the analog system. So in yesterday's lecture we have observed that we are intuitively, our systems, our senses, they are intuitively analog, but why we are using digital system, we'll try to answer this question in this lecture. Okay, so first thing, what we observe, what we see around the world, that almost all the matters have at least two states. So for example, if we see all the colors, we can classify them into black and white, although there could be various shades of gray, but yes, black and white could be one broad classification. Similarly, in electrons or protons, they either rotate clockwise or they rotate anti-clockwise. Similarly, if we see charged particles, either they are positively charged or negatively charged. And magnetic, also there are two poles, either north pole and south pole, or all the materials can also be divided into two classes: magnetic material or non-magnetic material. So this way, this two state classification is most easy thing to classify, and we can broadly classify anything into two classes. From there we can see, if we can represent all of these states into two states, we can call it binary. Binary means either the value would be 0 or value would be 1. So from taking clue from there, we can represent any particular state, any particular value using this binary representation. So in this binary representation, one digit would represent one binary number, which means either it is 0 or 1. Now digital systems are essentially electronic systems. Because digital systems are electronic systems, so they will talk in terms of voltages or currents. So let us say, because of the technology, mostly whatever we can safely classify them into voltage signals, let's say from now onwards. So we can say either a high voltage means it is 1 and low voltage means it is 0, or it could be vice versa also. So essentially there are two states: either a voltage is high or it is full voltage. Let's say the supply voltage is 10 volts. So this 10 volt would represent 1 and ground represent 0, or it could be vice versa, that ground represent 1 and supply voltage represent 0. So the idea is that we have two states in the system. One will classify as 1, another state will classify as 0. So what I would like to emphasize here, that it actually doesn't matter which state you classify as 1 or which state you classify as 0. Okay, so now if each digit represent only these two states, 0 and 1, if we combine multiple of such digits, for example, if we combine two digits, so they can essentially represent four states: 0 0, 0 1, 1 0, 1 1. We are also considering here permutations, not combinations. So essentially the position of 0 and 1 is important, or each bit's position is also important. So that means if you want to say how many number of states or how many number of possible values are possible using 3 bits, then it would be 2 is to power 3 because at any position there could be 0 and 1. Similarly, there are 3 such positions, so 2 is to the power 3 would be the total number of possibilities for a 3-bit 3-bit combination. So let's say if the group of bits are n bits, then those n bits can represent similarly 2 is to the power n states. Okay, so this is pretty much straightforward. So let's say if we try to define this n, let's say we want to see how many states or how many possible values could be represented using 10 bits. So we will do with the same formula 2 to the power n. So 2 to the power 10 possible values or 2 to the power 10 possible states could be represented. Now if you compute 2 to the power 10, then it will come out to be 1024. So for sake of simplicity, I am trying to simplify it into 1000. Okay, so now let's say if I have, instead of 10 bits, 1 bit means 1 digit, 1 binary digit. 1 binary digit is called 1 bit. Okay, so now let us say we have 20 bits. 20 bits could represent 2 to the power 20 states. And 2 to the power 20 states can also be written as 2 to the power 10 into 2 to the power 10. So that means although the number would be 1024 into 1024, but for again sake of simplicity, I can say that the number is approximately equal to 10 to the power 6. 1000 cross 1000. So 1000, when I am saying 1000 or 1024, this is in a decimal representation. Okay, so similarly, if I go for 30 bits, then for 30 bits, total number of states or total number of possible values would be 2 to the power 30, exactly 2 to the power 30. And again, if I approximate, then it is 10 is to the power 9. 10 is to the power 3, 1000 cross 1000 cross 1000. So that means 10 is to the power 9. 10 is to the power 9 means we call it 1 billion. So that means 20 bits could represent 1 million possibilities. And 30 bits can be used to represent 1 billion possibilities. And what is the population of India? Currently it is 1.3 billion. So if I want to represent all the population of India, then what I would require is essentially 31 bits. 31 bits would be sufficient to identify, to have an identification mark for each and every individual of India. Okay, so as a general knowledge thing, so you might also have heard some other notions of numbers here. So you might have heard some people, instead of bits, they write bytes. Bytes means 8 bits would be equal to 1 byte. Okay, and when you buy memories, these memories are also written as 1 kilobyte, 1 megabyte, 1 gigabyte, 1 terabyte. So 1 kilobyte memory means 10 is to the power 2 is to the power 10 elements. 2 is to the power 10 bytes will be equal to, so that means it's around 1000. So similarly, 1 megabyte would be equal to 2 is to the power 20 bytes. And 1 gigabyte is equal to 2 is to the power 30 bytes. Okay, so in other words, 1 kilobyte means around 1000 bytes, and 1 megabyte means 1 million bytes, and 1 gigabyte means around 1 billion bytes. Okay, so this is another parallel representation notions of words which we typically use for binary representation. Now this is the basic understanding of the binary representation. Now the question which we would like to answer in this lecture is that if we are given we want to create a digital signal, and as we understand from the last lecture, the word is essentially analog. So analog means it is continuous. It's continuous in values as well as continuous in time. So to represent, to see, to understand this particular fact in little more detail, let's try to understand using this curve. So let me see that this x-axis represent the time. So 0, 1, 2, 3, 4, 5, 6, 7 are different time units. This time could be seconds, picoseconds, millisecond, whatever, but they are discrete times. Okay. Similarly, values on y-axis we are representing values. Values could also be continuous, 1, 2, 3, 4, 5, 6, 7. So these are the values which are there in the y direction. And let's consider some particular signal which is given in this orange. Now we see this particular signal is essentially continuous in value. So value is somewhere between 3 and 4 when time was 0, and it was increasing, and when time was 1 it was around 6. So it is continuously changing both in space. In values also the values is continuous, and also with respect to time also it is continuous. Now when I am talking about digital signal, they are not continuous. Okay, neither continuous in values nor continuous in time, so they are discrete. Okay, so discretization would happen at both places, for values as well as for time. Now for example, at let me say discretization at time is happening at 1 unit of time. So at 0 unit of time, whatever was the value, closest value, so closest value is found to be 4. So this signal would be represented, because it is binary, so it would be represented by this combination 1 0 0. Okay, so after that we checked what was the value of this continuous signal at time equal to 1. It was close to 6. So the signal value would be now quantized at here it is very close to 6, so we took it as 6. So similarly at time equal to 2, again it is sampled. It's not 5, but it is close to 5. So it is closer to 5 than closer to 6. So we quantized means we said either it has to be 5 or 6, because it is closer to 5. So we made this digital signal equal to 5 at time equal to 2, and at time equal to 3, now it is closer to 2 then closer to 3. It was actually between 2 and 3, but it was closer to 2. So at time equal to 3 we said the value is 2, so on and so forth. So here we see for 4 as well as for 5, it was closer to 1 then closer to 2. So both at 4 and 5 we said it is 1. So it is interesting that the value was not 1 neither at 4 nor at 5, and there was a difference in value at 4 at time equal to 4 at time equal to 5, but both in digital world are considered to be same because they are quantized. Now this figure itself raised quite a significant questions for us. First question is that how can we make sure that this digital signal looks grossly inaccurate? How can we represent our system using digital signal? It doesn't look good, it doesn't look correct. So what should be done? So there are some theories. Most of you would be doing another course in parallel to this course, that's called Signal and Systems. So in Signal and System course you will understand more about this digitalization process or discretization process. But one important formula, one important thing which is called Nyquist criteria or Nyquist rate. So this rate proves that if we sample a particular signal at a particular frequency, any signal at a particular frequency, then it can be reconstructed back whenever we convert this discrete signal into a continuous signal. Okay, so it has been proved that if the maximum frequency of a signal is f, then and if it is sampled with the 2f frequency, then we can always regenerate without any loss of accuracy. So if our sampling rate is fast enough, if sampling rate is fast, so basically we are not sampling, we are sampling in such a way that the all minute differences are calculated or basically are captured, then we would be able to reproduce that. Similarly, discretization of value can also give a lot of errors. So if we can increase the number of such levels, so here number of levels are only 7, so if we can increase this number of level from 7 to let's say 100 or let's say 1000, then we would be able to capture each and every effect, and at sufficient number of times, if some sampling rate is good enough, then we would be able to, will not be able to miss any particular event in this particular in analog signal. So using these two important theoretical exercises, one is sampling at Nyquist rate, the other using very high like number of levels, using like more number of levels would increase the precision, so we would be more accurate. Okay, so this is the reason that we still like, although because of quantization there would be error, because of sampling there could be some error, but still digital signals seems to be more accurate, and that's what we seems to go. So you see there is a good paradigm shift also from going from analog to digital. So let's little bit understand one more thing, that intuitively when we see around world, it's not electronic, it's not electrical in nature. So essentially we see different physical quantities, different natural signals around us. These natural signals could be like we see things in terms of wavelengths or light, and we can measure lengths, or there are some kind of a pressure or frequency which we feel. Okay, sound waves are also different. So this natural or physical signals whenever we do any kind of electronic processing, first all of these signals are converted into analog signals. So there are various kind of sensors which are present. You have image sensors, like you might have heard of CMOS sensors which are present in your mobile phones or which are present in digital cameras. So the CMOS sensor will convert the light intensity, even RGB signals of each and every light wavelength. They formulate a corresponding electrical signals for that. Similarly, these microphones also have a diaphragm kind of a structure which convert the sound waves, which are essentially mechanical in nature, the sound waves into electrical signals. Pressure can be converted into using piezoelectric sensors to electrical signals. Similarly, there are thousands of sensors which are around us, and even in your mobile phone there are many sensors which are present, which try to measure the position or GPS or orientation, your speed. All of those things are finally converted into electrical signals, and these electrical signals are essentially analog in nature, means continuous in space as well as continuous in time. Now if we process these analog signals directly and give analog as a output, and then there could be a transducers and actuators which will finally convert into again back to natural signals. So for example, your speakers will again convert electrical signals into sound waves, or when we see in a monitor or a television, so this each LED pixels will have different color and intensity, which will again reproduce the visual effect of whatever we would like to see. Okay, and in mechanical, so basically again you can have stepper motors or different kind of motors which can put things into motion. So all of those things are again putting things into a natural signals. So this is the overall view of an analog system in which we are interacting with nature, or we are interacting with the real world. Now as we said, we are moving from analog system to digital systems because they looks like more accurate. So there would be additional steps involved here. There would be another component called this analog input would be given to analog to digital converter. So analog to digital converter, what it would do is it will do quantization, it will do sampling, and then For each signal, for each sample, it will give let's say a group of multiple digits or group of multiple bits as a digital output. So this digital input after ADC conversion, so this digital input would be discrete in time and values. Now digital system will process this digital input, and again using DAC, means digital to analog converter, will again generate an analog output, and this analog output would be again using transducers and actuators will be given back to physical and natural signals. So this is what your digital signal is. So essentially there would be two layers involved. One, there would be sensors which are converting physical quantity into electrical quantity, and then there would be an ADC which would be involved, then only you will get a digital input. Okay, so now again multiple questions arises here, that we are doing so much. Analog system seems to be straightforward, and they're also processing the analog which looks more correct because it is continuous in space and time. But why we are reading, why we are understanding this digital system? Is there any use? Is there any application? Okay, so to understand this question, instead of giving a theoretical answer, so first we'll see around us. So what we see, that there is a paradigm shift in last 20 years. So this in last 20 years we have seen, when all of you were kids, we used to have this CRT TV at our homes, but nowadays all these CRT TVs, first they have been replaced to LCD TV, now LED TV, and now most of us, whenever a new TV is being purchased, we are purchasing smart TV. Similarly, 20 years back we used to have these analog cameras. So these analog cameras, they used to click photo, and the photo would be now I will not say this was analog electronic signal, but it was still analog signal, because each photo was captured and then it was developed on a photographic film, and then you were creating from negative to your actual image. But now all these cameras are obsolete. You will not be able to see any analog camera these days. All the cameras have become digital cameras. Similarly, telephones have these dial-in telephones, where you used to dial each and everything, and they used to be connected using coaxial cable. Now instead of coaxial cable, now they are connected using FTTH, fiber optics cable, which is transferring a digital signal instead of an analog signal. So not only this, but all other things. For example, we used to listen to FM radio, AM radios. So all these radios also become digital in nature. All the mobile phones, they are the best example now. They are all completely digital. So when we see around, there's so many digital products, and all the analog products, they have been shrinking to very small market and a very small segment. Why it is happening? If it is so natural to grab, to catch, or to read an analog signal, why we are again processing into digital and then processing it completely in digital? Okay, so there are multiple reasons for that. One of the reason is, my digital system will give me very high accuracy. So let's take an example. So let's say my analog signal is between 0 and 5 volt. Okay, let us say the value is 3.5 volt. Now this 3.5 volt, if I convert this 5 volt signal into a digital signal which is represented by a 10 bits value, okay, so that means I would have an accuracy or precision of 5 milliwatt, and there is a very less probability that my 0 will become 1. So because 0 would represent 0 volt and 1 would represent 5 volt. So even though there is some noise or there is some environmental impact, chances that 1 will become 0 or 0 will become 1 is very very minimal. But chances, because of this noise, environment conditions, or transferring the value from one place to another place, because of the stray resistances, capacitances, there is a good possibility that this 3.5 volt will become 3.6 volt or 3.2 volt. Okay, so because of all of these things, because of all these stray electrical circuits, stray resistances, capacitances, because of this noise, there is a good possibility that electrical signal, analog signal will change its value, but a digital signal will not. The other thing on top of that is that, let's say a digital signal is being transmitted from one place and traveling to the other place in a channel or basically in a wire. Now if we see that there is a possibility of changing from 1 to 0 within this particular wire, then there could be some system called error control codes, error correction codes. So we can identify if there is some bits flipped from 0 to 1 or 1 to 0, and we can even correct them. So those encoding can be associated with binary. So that means even though there is a possibility of inaccuracy, we can again correct them. The other biggest thing is programmability. Now your analog signals or analog systems, when they are created for one particular use case, one particular using the fundamental resistors, capacitance, and their value of resistance and capacitance also matter. But digital systems, they are created using generic gates. So once they have been created, there could be various mechanism. Using them, they can be reprogrammed. Now reprogramming is a very important thing for today's world, when we are changing very fast. So for example, you get this Android updates once in 6 months, because you would like to get new features every time. And also there is a possibility that there are some bugs in your system, so there is a possibility of patching. So there could be you can program, or as the functionality will change, you would be able to change yourself. Okay, so this programmability in this ever changing world, and this ever changing world is more changing, dynamically changing these days than it was in past. Okay, the other thing is you see, there is a effect of environment. So for example, temperature is increasing, humidity is increasing. Because of that, electrical properties of your basic circuit like resistance, capacitance, inductance, they will also change. Okay, but my digital systems are digital bits are essentially more robust to change. So that's why they are more maintainable. So after 20 years, after 10 years, also they will function correctly. They will not give some error. But there is a possibility that your analog system will not run for that long. Okay. So if there are so many advantages, there must be some disadvantage also. Your analog design are usually very small with respect to digital design. So let's say if I want to do multiplication in analog, it could require only 20 transistors. But if I want to do same multiplication in a digital domain, then I might require 10,000 transistors. So the cost could be 100x or 200x in case of digital. So because more number of transistors are required, it would be costly, it would be slower, it would consume more power. But it is going to be accurate, it is always going to reproduce the same value, whatever be the case. It is, you can change, you can program it over the time. So even though digital signals are slower, we consume more power, are less area efficient, but still they're more prominent because they're reproducible, because they're more accurate, because they're programmable. And most importantly, over all of them, design automation gives another cherry on the cake, that we can automate. So we can design digital logic using thousands or millions or billions of gates. So we'll see that in the next slide. So the conclusion of this slide is essentially, although most of the systems are going toward digital, but if I require very area efficient and very high frequency, very high bandwidth requirement operation, then it is still done using analog circuits. So for example, your amplifiers, your input output circuits, and plus your radio RF receivers, so they are all will be analog. They are analog in nature and will remain analog in future also. So design automation, or like huge quantity, we'll see. So another important thing we see that so there's one particular law which is pushing the growth. So we call it Moore's law. According to Moore's law, every 18 months number of transistors on an integrated circuit will double. So your area remains same, but the number of transistors within the same area would be doubled after every 18 months. All of you know that anything which is exponential in nature will not work, but this particular law, this particular Moore's law is stable. It is working at least for last 40 years. So if we see our first integrated circuit in 1970, so till 1920, we see that all of this blue dot represents some of the production ASICs. So number of transistors are doubling every 18 months, and this doubling is happening because of technology, because of compute requirements, so because of marketing requirements. So every time we would require a newer circuit or a circuit with a new functionality. So because of these requirements, technology is also pushing itself that we will bring all these transistors, more transistors into same area. Okay, so it is shrinking. You might have heard that now latest transistors or latest chips are fabricated onto 14 nanometer. Previously it used to be 28 to 22 nanometers. So every time they are shrinking by a newer technology or a smaller technology. So because of that, now more transistors can fit into this, and the other side effect is that now we need to design a chip which would have billions of transistors onto the same chip, and that could happen because of design automation. So because of all these 3-4 things, that compute requirement keep on changing, we always require new smartphones with new features, more features, and because technology is improving itself, and because now we have techniques which partially we'll study during this course, that can we automate, given a specification, can we design our digital system automatically. So because these techniques are there, now we can even scale up, we can design even or ever complex chips. Because of this particular dynamics, that design could be automated, now we can fabricate more complex chips, and this is also one of the reasons that digital revolution is replacing all the analog products. And this digital revolution, as we discussed in our previous lecture also, this digital revolution is also pushing the boundaries and is or will be causing fourth industrial revolution, that means due to your machine learning, artificial intelligence, and IoTs. So with this I would summarize the lecture, that so in today's lecture we have understood how we sample digital signals and how we quantize them, or how we actually get digital signals from analog signals. And we have also we have seen the overview of analog and digital systems, what are their input output comparison, why digital systems are more robust than analog counterparts. So with this I would like to close, and we'll see you in the next lecture. Thank you very much.